Hello, and welcome to today's on Semiconductor Technology webinar. Our topic today is transfer molded power integrated modules for industrial drive. I'm Chris Kosters with On Semiconductor, and I'll be your moderator today. During this webinar, the presenter will pose a few poll questions. Please note that the response options for the poll will become visible on the right side of your screen, where you can submit your response within the time frame of 1 minute. At the end of the webinar, we'll be holding a Q&A session. During the webinar, please open the Q&A window on the right side of your screen and send your questions to all panelists. This webinar will be recorded and posted at onsemi.com. You'll be notified via email when the webinar is available. Now let's meet today's presenter. Guillaume Gargallo works as Product Marketing Manager in the Power Solutions Group at On Semiconductor. He is responsible for driving demand creation at focused industrial accounts in EMEA, and he supports the BUs with the definition of new products. Now let me turn things over to our presenter. Guillaume, the floor is yours.
Thank you, Chris. And welcome everybody to today's webinar. So as Chris mentioned, I will be introducing our new transfer molded power integrated modules for industrial drives. So before we start with the topic, let's talk a little bit about industrial motors and why onsemi is the right partner for your motor drives applications. So motors have become a key element in this industrialization, improving productivity and enabling also more sophisticated products that have improved our lives significantly. At the same time, the motors have become one of the major energy consumers, being responsible for nearly 1/3 of the world's electricity consumption. It is also expected that the usage of motors will continue increasing in the coming years. And for that reason, the improvement in motors efficiency has become a major concern for policymakers. And this, of course, will continue boosting the inverterization of the motors to be able to increase the efficiency. At the same time, other market trends are boosting the usage of inverters in motors. This is, for instance, the further automation and robotics growth, as well as the redundant supply chain, and in the later years as well, the automation of warehouse management. So the motors can be found in a wide range of applications. Besides the industrial robots I've already mentioned, we have here as well the variable frequency drives, we have the compressors, pumps, fans, and so on. At onsemi, we provide the full portfolio of products for the motor drives, including not only the IGBT modules, but also small signal components, operational amplifiers, and pretty much everything you can find in your PCB. We have a very strong focus on the industrial market, where we are a leading manufacturer in terms of quality and supply chain. And as I mentioned, we have this very broad portfolio, as well as several years of expertise in this market. So now let me introduce the agenda for today's webinars. So I will start introducing our TM-PIM package, transfer molded PIM. Later on, I will discuss some of the thermal performance features of this package, moving in direction reliability and safety features. And I will continue by introducing some of our selection and design tools. And I will finalize with a quick introduction to our roadmap and product portfolio. So what is a TMPIM? A TMPIM stands for transfer molded power integrated module. The PIM is the integration of several components within one package. And in this case, typical for motor drives applications is the CIB circuit or converter, inverter, and brake. So this is all integrated within one module. TM stands for transfer mold process. This is the manufacturing process, and this is the new part of this package for this power range, where in one step we have the full molding of this package and encapsulation. So how does it look in terms of manufacturing process? So this is a quick and an overview of how our manufacturing process looks like for a transfer molded pin. So we start with the substrate separation, where later on we print there the first layer of solder. And in the next step, we attach the components. So the main dies, IGBTs, diodes, and eventually also silicon carbide MOSFETs, for instance. Later on, and here's where one of the main differences to traditional gel-filled modules comes, we have here a single lead frame that is attached to the DCB. And later on, we move to the wire bond, which is also common process in other types of packages. And in the end, also another differentiating process in this case, we have the epoxy encapsulation when in one step, we fully encapsulate all the components of the package. So before we move forward, I would like to ask you a question to see also which audience we have here today. So what is the most important factor for you during the selection of a power module? Is it the high performance in efficiency and power density? Is it the robustness and long lifetime? Is the cost price per kilowatt ratio? Or it's more an easy designing and also future power scalability with the same platform? So let's see, you have your questions on the right-hand side of the screen, and you have 30 seconds left to answer. And later on, Chris will update on the results. So let's see which audience we have here today. Okay, so it's 10 seconds left. Good. Okay, so let's see what are the results.
Okay, thank you, Guillaume. So the poll closed, and it looks like for the question, what is the most important factor for you during the selection of a power module? 32% of people are saying high performance in efficiency and power density. 36% say robustness and long lifetime. 24% cost per kilowatt, and 8% easy in design and future power scalability. Now, Guillaume, what do you think of these responses?
Yeah, so this fits also with what I will be showing later on. So we will discuss the high performance in efficiency and also power density of the package. And definitely a key topic of the today's webinars will be the robustness and long lifetime for cost and price per kilowatt. So this we can continue discussing after this webinar when we can engage with some opportunities. So let's move forward with the introduction of the transfer molded pin. So what are the main features of this package? So besides the transfer molded process that I have mentioned before, so what does it mean in terms of features? One of the key features of this process, it enables the extension of temperature and power cycling capability. So you can see here on the right-hand side the structure of the package. So we have significantly less components than in traditional silicon gel modules. And besides, this is all encapsulated with this epoxy resin, which enables also higher withstand capability for environmental hazards such as high corrosion or also humidity. It also helps to keep the bond wires, for instance, better attached to the die, extending this lifetime. We provide here not only the standard aluminum oxide ceramic, we have also some versions with what we call advanced substrate technology. I will show later on a bit more in detail what this means. This enables a reduction in the RTH and therefore also the increment in the power density. An important feature here is that we can keep the 6 millimeters distance creepage between the lead frame or the pin terminals and the heatsink. So in the end, the benefit for you is here an enhancement of reliability and lifetime, even in harsh environments, as I mentioned. We enable here a full design flexibility. We have a different packages, different current ratings covering the full power range in the same package. Also, the better RTH, it will enable a lighter cooling, which at the end comes also to more compact devices. We have initially here two packages that have been released already. This is the DIP26 package and the QLP74 package. So this is a dual inline package, which and whereas this is a 4, so it's using pins in all 4 sides of the module. And later I will show the lineup for these two different packages. So how does it differentiate the transfer molded PIM from the gel fill? Besides the process I've mentioned before, let's take a look at the different components that are included here in each of these packages. So on the top, you have once again the cross section of the transfer molded PIM. And here we can take a look inside the module. So how does it look like? And regarding the components, we have here the lead frame. This is something that obviously is different than a traditional gel fill module. We have the DBC. We have the different semiconductors, IGBTs, diodes, or other kinds of semiconductors as well, which will be later attached here to the pin terminals and between the copper tracks and also the dies with the aluminum bond wires. We have, of course, the solder material between the semiconductors and the DBC. We include in every one of these packages an NTC, a thermistor, and then later on this will be encapsulated with the epoxy. If we take a look to a gel fill module, besides having these steps in common, so the DBC, the IGBTs, bond wires, solder, and thermistor, so this is in common with the transfer molded PIM, we have a significant amount of pins, independent pins, and not just a lead frame. We have also here the glue between the DBC and the plastic housing. Of course, we have the silicone gel, and then we have the housing as well. And later on, we have as well the base plate in some cases for gel fill modules. So all in all, we have a much more reduced BOM for the transfer molded PIM, which at the end makes the production process more stable. And also here we can increase the quality of the product with this higher process reliability. As I mentioned earlier, we have here two different substrates. So when we look at the structure of the standard and this enhanced package, we can see here the difference where we have in the DBC the thin copper layer, a thicker ceramic, and then again a thin copper layer. Whereas in the advanced or enhanced transfer molded PIM, we have here a thicker copper layer. We have also an advanced ceramic substrate, which is significantly better than the standard aluminum oxide. And later on as well, we have here a thicker copper, which all in all will improve significantly the RTH of the package. This allows us to put more power in the same footprint. So then, this being said, let's take a look more in detail to the thermal performance. And here we can see that when we use our advanced substrate, we have a significantly better RTH compared to a base plate package from other vendors with a silicone gel filled package. And you can see in every single one of the components in the IGBTs as well as in the diodes, we have up to 30% improvement in the RTH. This in the end can lead to either a longer lifetime if you decide to keep the same junction, the same output power, or you can increase the output power keeping your lifetime. So if you are satisfied with the current lifetime of your product, this is okay. With the transfer molded PIM, you can keep that lifetime but increase the output power, which at the end also we can fit up to 65% higher current density, not only because of better RTH, it's also due to the smaller footprint. As you can see here, the transfer molded PIM is significantly smaller than a base plate package from standard industrial packages in the market. Here we have also done a power recycling test to compare our performance to that of, in this case, a base plateless package. And here we have put one of our TM-PIM 6-pack package with 35 amps in a power circulating equipment together with the competitors as 35 amps package. And in the end, we can see that keeping the same ambient temperature, we can achieve a much lower heatsink temperature with our module for the same test conditions. This is related to different factors. One of them is the higher efficiency, rate contributed by the faster IGBT and fast recovery diode characteristics. This is one side. The second part is also thanks to the lower RTH. The TM-PIM results at the end in a better heat dissipation, and we can keep a lower heatsink temperature for the same conditions. Also, if we compare our transfer molded package to a base plate again, we did here some simulations where we built a complete 3D model of our transfer molded PIM and compared to a base plate package with a 3mm copper base plate. So here we took in the first stage our standard transfer molded PIM, and here we can see that the maximum junction temperature for the same operating conditions is significantly higher than a base plate package. So far that's normal. So with the base plate we can achieve, of course, here a better thermal spreading. But of course the base plates come at a cost, and also it adds an additional layer where it might be a critical point for reliability. So if we get rid of the base plate and we use our enhanced DBC substrate, we can achieve under the same conditions the same junction temperature than a base plate package, of course at a much better reliability, because as I mentioned, so we reduce one of the critical components for reliability, which is the joint between the base plate and the DBC. So we will start releasing products in our QLP series in using our advanced substrate, and we already have products in the market in our using our DIP series, which is rated up to 50 amps in CIB configuration using the enhanced substrate. So with this product, you will be able to achieve better performance than a base plateless gel fill module and a similar output power capability than a base plate package with a gel fill technology. So now I will introduce some of the reliability and safety features, but before I move into that, let me ask you another question. So which is the main failure mechanism in the power modules used in your application? So is it often a long-term power and thermal cycling limitations of the package and technology? Is it failure related to harsh environments such as humidity or corrosion? Is it more often electrical overstress, or is a power module manufacturing defect? So once again, you have some 30 seconds left. You can find the answers on the right-hand side of your screen. So looking forward to see the results. So let's see, 15 seconds left. And later on, of course, we will touch all these different topics that are mentioned here.
Thank you, Guillaume. So the poll is about to close. And it looks like for the question, which is the main failure mechanism in the power modules used in your application, 40% of people are saying long-term power or thermal cycling limitations. 10% are saying failures related to harsh environments such as humidity or corrosion. 43% say electrical overstress, and 3% power module manufacturing defects. So what are your thoughts on these responses?
Okay, that's an interesting result, especially regarding the electrical overstress. So today I will be focusing more on the package perspective, of course, for the electrical overstress. There we have a very rugged IGBT technology. But since today we are introducing the package, I will focus more on the long-term power and thermal cycling limitations, which we heard is one of the main concerns for our audience, and also failures related to harsh environments, humidity and or corrosion. So let's check some of the reliability features of this package. And one of them is the enhanced temperature and power cycling capability. This is mainly related, of course, to this epoxy encapsulation, as well as the material selected for our packaging technology. And one of the tests we perform here, it's a temperature cycling test where we move here between -40 and 125, and then we repeat this test continuously, and then we analyze how this influences the different parts of the module. So here you can see on the top is our transfer molded PIM. In the middle, it's a gel film module without the base plate, and then on the bottom we can see a gel film module with a base plate. So of course, in initial stage of all the modules show no signs of delamination whatsoever, so it's a very nice picture in all three cases. Then we start doing the temperature cycling, and already after 100 cycles of this -40 to 125 degrees, we can start showing some slight signs of delamination in the base plate module, in the joint between the DBC and the base plate, as well as a little bit here as well in the gel film module, in the joint between the dies and the DBC. If we continue with these cycles, after 500s, we can see in the transfer molded PIM there is still no sign of delamination. On the other hand, already in the gel film module, we start seeing stronger signs of delamination in some of the layers of the DBC, as well as in the solder between the die and the DBC. And in the base plate modules, we can see already the lamination is pretty considerable, especially in the edges of the different DBCs in the joint between those DBCs and the base plate. Continuing with the cycles, we stop after 1000, where we can see no signs of delamination whatsoever on the transfer molded PIM. The picture looks very similar to the initial one, if not the same. And here we can see in the gel film module without the base plate, there is a strong delamination on the die attach. And at the same time, in the base plate modules, we can see in some areas there is even almost no solder material left between the DBC and the base plate. So this is already a strong sign that for a temperature cycling, the transfer molded PIM with the existing technology has a much better performance than some of the gel film modules available in the market. At the same time, we perform here lifetime power cycling test, where we have in a very short time, 4 seconds, a very strong current to achieve a very high delta T. So here we have 3 temperature ranges that we tested, and from there is extrapolation of the lifetime curve. One is a delta T, 100 degrees C, so coming from 25 degrees C in the heatsink, and then heating up the dies up to 125 degrees C. Then we have the same for 125 degrees C delta T and 150. And here we get a very good lifetime curve, which compared to some of our other gel film modules, it can extend the lifetime significantly. Of course, this will depend on the semiconductors used as well, on the die size, but we can see here a clear improvement compared to other technologies that are being used for power modules. Regarding standards and certifications, so our transfer molded PIM is designed to meet the IEC 61800-5-1. This means that it also can meet the clearance distance requirements from the pins to heatsink, as well as the package materials is a CTI 600 which also enables us to meet the creepage and clearance distances between the different potentials from the different pins, reducing also the module size. And of course, our modules are in line with the UL 1557 in terms of production test. And we have here also the UL certification where you can check later on the file as mentioned here. Then an additional concern here is often for baseplate-less packages is the strength of the ceramic in terms of ceramic cracks. And here what we wanted to prove is that with this package, we have a very good control on the warpage of the ceramic, as well as a very rugged structure. So we printed here a very thick layer of silicon grease with 200 micrometers. And then we mounted the screws using relatively high torque, and then analyze whether we can see any signs of ceramic crack by, for instance, doing a high pot test. So after doing this test with several packages by following the procedure mentioned here, so first attaching with a small torque, two sides, first one, then second, and then finalizing with the final screw torque at different torque values, so from 2 Newton per meter to 3. And we have here no signs of ceramic crack whatsoever. So this demonstrates as well the ruggedness of this construction for assembling the package in a heatsink. Then let's move a bit forward. So how can we support you as well to designing this package? So with this, we have brought to the market some selection and design tools. But before I go into this, let me ask you another question. And this is, which of support tools are more helpful for you when designing a power module? Is it a software simulation tool? B, application notes with in-depth technical explanations? You would prefer to have a plug-and-play evaluation board? Are the webinars and online trainings helpful for you? Or you just like to have all of the above? So again, you have here on the right-hand side different answers. So we're used to see again the results. And of course, as you can imagine, we are working to meet all of them. But let's see, it's interesting for us to understand also what is more useful for you and how can we support you better to designing our components. Okay, Chris. So.
Thank you, Guillaume. So yeah, time is up. So let's see what the answers are for your question. Which support tools are more helpful for you when designing a new power module? So 9% of people are saying software simulation tools. 36% are saying application notes with in-depth technical explanations. 3% plug and play evaluation boards. Again, 3% say webinars and online trainings. And then 48% are saying all of the above. What do you think of these responses, Guillaume?
Yeah, that makes sense. So it's good to have the more tools you have to design in, then of course the easier it makes it for you. And we are definitely working in all these 4 fields. I will show you today a couple of them. And for the application notes with in-depth technical explanations, we are working to launch more and more application notes that will be available on our web, and we have some of them already available. So just first, maybe quickly to review what is the application scheme of this transfer molded PIM in this CIB configuration, and also which products we have available for approximately which power ranges. And once again, so the CIB, this is converter, brake and inverter, or converter-inverter-brake configuration. We are launching here both 650 volt CIBs and 1200 volt CIB transfer molded pins for different output voltages. And the brake is an option, so we also have a CI modules, as well as the full 6 packs will come later on. If we consider only the CIB modules, we have launched so far 25 to 50 amps CIBs, which approximately, of course, always depending on the thermal design, covers power range from 5 to 10 kilowatt. And we are starting to sample also 75 and 100 amp CIB in the QLP package, which will cover approximately, again, all the way up to 20 kilowatt. So one of the main design tools that we have released is our online simulation tool. And here you can go to our website. Here you will find it easily under this power supply web designer. We have what is called a motion control web designer. And once you click there, you will go to a set of interactive questions that are, of course, linked to the application. And this, in the end, will help you to calculate the losses, as well as support you to check the heatsink characteristics to use the transfer molded PIM in your motor drive. So if you go there, you just click here on this motion SPM and IPM design tool. Once you are in there, you will have to enter the application parameters, RMS current, DC voltage, switching frequency, and so on, so standard application parameters. Then continuing with this, you can go, there's a wide range of packages. Most of these are IPMs, which is also another product line we are offering. And here you can see already available the Deep 26 package, which is the smaller transfer molded pin that we are introducing here today. And once you're there, you have all the available package. So you just need to select the part number you want to analyze, and then just click forward to analyze design. And you will go directly to the results where you can get a reminder of your input and output conditions. And here you see all the different relevant outputs, such as losses, junction temperature, and so on. And there is a set of graphics that will help you to better understand what are the losses. We can also simulate overload conditions and so on. And in the end, you can download this as a full report where you will get all the results. In addition to this simulation tool, as I mentioned, we have online some application notes already available, and we are working on more of that. And an additional design tool that we are now releasing is our new motor development kit. And this is a versatile and comprehensive development kit tool where we have a combination, is a two-layer tool where we have a control layer with a universal control board for a different power layer, so different power boards. Each one of these power boards is used to analyze different products. So we have already available 2 boards for IPM. So this is for up to 1 kilowatt. And then also we just recently launched this 4 kilowatt power board for our SPM31 IPMs. And now we are working to release as well the power board for our transfer molded PIM up to 10 kilowatts at the moment. This will be available in Q4. So with this, we can have a universal, let's say, environment for all the different power boards. This will enable us also in future, and also our customers, with a similar set of control features to analyze different power boards and different product lines. Okay, so now let's take a look to the roadmap and the available product portfolio. So here, a high-level overview of the different products that we have released, that we are sampling, and also that are currently under development. So we have here 3 different configurations. We have CIB, CI, and then also the 6-pack in 650 volts, as well as in 1200 volts. And this combined with the 2 packages I've mentioned already today. One is the DIP26, and the second is the QLP24. So if we look at 650 volts CI and CIB, we cover up to 50 amps with our standard DIP26, and 75 amps with our enhanced DIP26. We are also starting to sample as well here up to 150 amps with our QLP74 package. The QLP74 comes in all cases with our enhanced DBC. Then we have here the 650 volt 6-pack currently under development. This will cover from 100 to 300 amps in these two packages. And then we have the 1200 volt portfolio, which is already released in the DIP26 for 25 to 35 amps with standard DBC and 35 to 50 amps for the enhanced DBC. And then we have here as well sampling 75 and 100 amps CI and CIB modules in QLP74. Finally, we started the development as well of our 6-packs in 1200 volts. Initially, we have 75 amps for the DIP26 and 150 and 200 amps for the QLP74. So then here is also a summary for the DIP26. I've just mentioned the different products in the lineup. So just a quick reminder about the features. So besides this being a transfer molded process package, we have here as well very rugged 1200 volt and actually 650 volt high performance field stop 2 IGBTs integrated with a CIB configuration as well as CI and in future the 6-packs. And the pinout is also relative, has the same relative position to available packages in the market. This is also to make it easier for you to redesign your PCB. So you will find the different potentials in the same relative position as of industry standard package. So with this, we expect to have help you to improve significantly the reliability and the lifetime of your product. As we mentioned before, so because of the epoxy encapsulation, the package is very resistive for environmental hazards like corrosion or humidity. And we will line up this complete portfolio so you can scale up different current ratings. And thanks to the keeping the distances between the different potentials, we can enable also here a 2-layer PCB. This is the last point I've mentioned. So you have here the safety distances between the different pins. So in all cases, we can meet the different requirements for distances between pins and potentials. And this also, of course, considers the solder pad on the DBC, on the PCB. And by this, at the end, we can enable a 2-layer PCB. So this dual inline pinout also make it very easy for the layout of the PCB. And there is a DC plus and DC minus crossing with the width of the module. This is to minimize also the parasitic connection. And of course, as we mentioned before in the safety and standards, this is designed according to IEC 61800-5-1. For the QLP series, so it's a similar sets of features and benefits. You can review here again the lineup, so 1200 volts, 75 and 100 amps for CI and CIB, and 150 and 200 amps for 6-packs. And with the 650 volts, we can of course go a bit higher in the current, up to 150 with the CIBs and up to 300 with the 6-packs. In this case, we have a quad-lit pinout with again the same relative pin position as industry standard packages. And in this case, also we can enable, thanks to the configuration as well as the CTI 600 materials used in the encapsulation, we can enable this increased terminal to terminal distances, which enables you to use thicker PCB coppers, and then, of course, as I mentioned before, reducing the amount of layers, which at the end results in a cheaper PCB. So we have, as I mentioned, the full power spectrum, and this is under the same pinout, so it's very easy for scaling up all these different solutions. So let's review the key takeaways before we start the Q&A session. So now we have released a new and innovative transfer molded PIM platform. This is integrated with an optimal IGBT and fast recovery diode technology. And thanks to this, we can achieve here a high efficiency and robustness, which makes the package very suitable for motion control and, for instance, HVAC application. So with this built reliability of the substrate and the epoxy transfer molded technology that we have mentioned during the webinar, we enable here better thermal and power cycling capability. And this results at the end in a longer lifetime and also higher reliability, enabling, for instance, less maintenance and operating cost. The thick copper advanced substrate eliminates the base plate, which extends in the end the power density as well as improves the thermal resistance. Also, the epoxy encapsulation makes the module hermetic, and this also combined with a nickel plated substrate makes it very resistant against environmental hazards such as corrosion as well as humidity. The package is designed to meet all the different standards so IEC and UL, and we are launching more and more transfer molded PIMs, so stay tuned to our website. We'll come with more products soon. And with this, Chris, I move to the Q&A session. So thank you everybody for listening. Looking forward to your questions.
Thank you very much, Guillaume, for this excellent presentation. So during this presentation, we have received a number of questions, so we will jump right in. If you would still like to submit any questions, please open the Q&A window on the right side of your screen and send your questions to our panelists. So Guillaume, a first question for you. Is the transfer molded PIM concept going to replace the gel-filled module portfolio from ON Semiconductor?
Right. So as you know, so ON Semiconductor also offers the gel-filled modules. And the short answer is no. So this will not replace. I think there is still a market area where both types of modules can be a good fit. So in this case, we are mainly launching the transfer molded PIM for initially motion applications, motion control applications. The gel-filled modules offer the advantage of a PIM flexibility, which makes it very suitable for applications where high complexity in the topologies is needed, as well as high switching frequencies, for instance. So we can play with the PIN arrangement and reduce the inductance there, stray inductances. So there is still place for both types of packages in the market.
Okay, thank you, Guillaume. Next question for you. I haven't had any reliability or lifetime issues using gel-filled modules. Why should I change to this newer platform?
Right. So, so I put some emphasis today on the improvement in reliability of this package. Of course, the reliability has two phases. One is extending your lifetime, but then the second one, if you are satisfied with the current lifetime, this is also okay. The second side of higher reliability is also it enables a higher power density for the same lifetime. So you can go higher with the junction temperature and then keep the same lifetime. So of course, higher junction temperature in the end means higher current, higher power density.
Thank you, Guillaume. Next question for you. Any plan to release this family of modules for the automotive market?
So we have already transfer molded packages for the automotive market. So today we are covering the industrial market. These packages are initially not qualified for automotive, but we do have in ON Semiconductor and standard portfolio of transfer molded packages for automotive. So I recommend you to check on the website or with your sales representative, and they can give you an update on all the portfolio for automotive modules.
Okay, thank you, Guillaume. Next one for you. How can I get the evaluation board for the transfer molded PIM?
Yeah, so the evaluation board will be available by end of Q4, and then you can contact either your local or regional sales representative or your distributor. We work with many distributors, so just contact them. The board will be available most likely end of this year.
Thank you. Next question. Do you plan to have IPM in these packages too?
IPM. So we have several IPMs with similar packages. So the specific design of this package does not enable to having the drivers inside, but our standard IPMs are very similar. The technology is also a transfer molded, so you can have there. We have a very wide range. We are actually a top supplier for IPMs, so I'm sure you will find the right fit for the application.
Okay, thanks, Guillaume. Next question. In the roadmap, you showed products using IGBTs. Is there any plan to release this package with SiC MOSFETs?
So one of the main characteristics of this package is the enhanced reliability. And one of the main headaches when designing silicon carbide is the lifetime. There's silicon carbide is a very small device where you have the losses very concentrated. And of course, even if they perform much more efficiently, at the end, you have it very concentrated in a small surface. So therefore, this makes the package a very good fit for a silicon carbide where we can improve the reliability of the semiconductors. So I would expect that some products with silicon carbide MOSFETs or diodes will come to the market soon using this package.
Okay, thank you. Then it looks like the last question. Besides industrial drives, in which other applications can I use the transfer molded PIMs?
So initially we have now released the products in a CIB and CI configuration. This is the typical one for industrial drive. We are now finalizing the development for the 6-packs. And once the 6-pack is available, there is no limitation on which application can use this package. So any application with a DC to AC conversion or even AC to DC bidirectional, where a 6-pack is used, this package would be a good fit. So this includes HVAC or other kinds of applications. So there is no limit regarding the application.
Okay, thank you, Guillaume. That are all the questions that we have received. So I think hereby we can close this seminar. So on behalf of On Semiconductor, I would like to thank everyone for attending, and I wish you a nice rest of your day.
Thank you.
Thanks a lot.